Okay, so consider a function of two variables x and y where you get 2x minus 3y as the first coordinate and negative 2x minus 3y as the second coordinate. Now in general, if you have function of two variables that looks like something x plus something y without any constant term, something x plus something y, that will be an example of what's known as a linear operator. Okay, linear operator. Now we can rewrite the function t as the following. So think about this. If we have 2, negative 3, negative 2, negative 3 times xy, do this calculation. What do you see? I'll cross down, so that gives you 2x minus 3y. I'll cross down, that gives you negative 2x minus 3y. Oh, that's exactly the same as this guy, right? And in such a case, we say t represented as matrix relative to so basis E is going to be our standard notation for the standard basis for R2 or R3 or in general Rn. So what's the standard basis for R2? 1, 0 and 0, 1, right? So it's the same idea. And we write that t is represented as, so whenever I make a representation, I'll try to use square brackets. It doesn't have to be. I still don't know what's the standard for matrices, whether parentheses or this. All the linear algebra books, they use both. All right, so we write it as 2, negative 3, negative 2, negative 3, and E, just like that. Okay. Now let's try to investigate what the properties of these numbers are. Okay. So if I do, so I'm going to use this another standard notation where we write E1 for this guy and E2 for this guy, okay? That's a standard notation. So, what is T applied to E1? Okay, what is E1? E1 is 1, 0, which means 1 goes into X and 0 goes into Y, right? So what do we get if we calculate that? What do we get? 2, comma, negative 2, right? And that can be written as 2 times E1 minus 2 times E2. Is that right? Because E1 is 1, 0 and E2 is 0, 1. If you replace E1 by 1, 0, E2 by 0, 1, and you simplify, you get exactly this, okay? All right, and then what about T E2? Well, it's T 0, 1. That gives you -3 comma -3, right? And that's -3 times E1 minus 3 E2. And once you find out this, you see that the numbers 2 and -2 are, so this vector right here, let's call this V1 and call this V2, and you see that V1 is this guy and V2 is this guy, right? You just write these numbers vertically, and that's the matrix representation. Is that good? All right, so question. So with the same T, let B be, let's use 1, -1, and 1, 1. Okay, it's not so hard to check that these are linearly independent. In fact, this is like 2 dimensions, so in 2D, as long as you have 2 vectors that are pointing different directions, they will be linearly independent, right? This one is like pointing that way, this one is pointing that way, so this is V1, that's V2, that's what these are. So definitely linearly independent, and since this is going to span R2, if you have 2 vectors that's inside R2, that's linearly independent, that should be forming a basis. Okay, so that's our basis, and we're going to ask find matrix of T relative to B. Okay, that turns out to be harder question, but the format is exactly the same. The way you're going to do this is, if I call this, so now let's call this, since I already have V1 and V2, just in order not to confuse ourselves, let's call this U1 and U2, okay? So the plan is like this. You want to find T of U1 equals to something times U1 plus something times U2. And then T of U2 equals to something times something times U2, U1, plus something times U2. Okay? And once you find A, B, C, D, then the resulting matrix should be A, B, and then C, D. Remember, these should be vertical vectors, okay? So that's the answer that we're looking for. So let's try that out. Okay, solution. Okay, what's T of U1? T of U1 is 1, -1. Okay, what is that?
5.
Okay, 5, and then 1, -1. 1, right? Now I need to rewrite this as something times 1, -1 plus something times 1, 1. Let's see, that means I need A plus B has to be 5. A plus B has to be what? has to be 1. If you add them, then you get 0, you get 2b equals to 6, so b must be 3. Plug that back in here, or maybe here, then a must be 2. Okay, so I get 2, 1, negative 1, plus 3 times 1. Okay, since I'm not so sure, let me give you time to do the second one. T of u2, which is a 1, 1. Okay, so find what T of 1, 1 is, and again, try to find two numbers so that the resulting vector is a linear combination of 1, negative 1, and 1, 1. So let's try this together. What is T? T takes in two values, x and y, and spits out two values, right? In other words, T is a function from R2 to R2. That's what this is, right? And whatever you plug in, all you have to do is just plug in those numbers to calculate this. So it's going to be 2 times 1 minus 3 times 1, negative 2 times 1 minus 3 times 1. And that's going to be 2 minus 3, negative 2 minus 3, which is negative 1, negative 5. But we don't stop there. In order to get the matrix representation relative to the basis B, we have to write it as a linear combination of our basis B. So the basis B is 1, negative 1, and 1, 1. Simplify this, what is this? C, negative C. If you multiply C here, multiply D here, so D, right? And if you add these two, you get C plus D, negative C plus D. Okay? And that has to equals to negative 1, negative 5. So that's going to give you C plus D equals to negative 1, negative C plus D equals to negative 5. A quick way to calculate this is to add them. You get 2D equals to negative 6, which gives you D equals to negative 3. Plug that back in here, you see that C has to be 2. Okay, so the result that we get is, so first of all, T of U1 is equal to, we found out that's 2 times U1 and 3 times U2. And T times U2 gives you 2 times U1 minus 3 times U2. Therefore, T, if you use basis B to represent, you now have to put these two vectors as column vectors. So this 2, 3 goes vertically, 2, negative 3 goes vertically. Okay. So that's what it is.